In the previous segment, we learned how to convert an infix notation to its postfix form. In this segment, we're going to learn to do the opposite. That is, we will be given a postfix expression and we will convert it to its infix form. So if my infix is a minus b, then the postfix will be a b minus. So if I have a b minus given, I will have to convert it to a minus b. So for this process, we can also use a stack and do the conversion. Now we will convert the postfix notation a b minus to its infix form. And we already know the answer. It should be a minus b, not b minus a. So the order of the operands is very important because a minus b and b minus a are not equal. So if I have a minus sign over here, this means a minus b should be its infix form. So the rule is I will parse through my postfix expression, and when I see an operand, I will push it inside the stack. So a is an operand, it will be pushed inside the stack. Then I have b, this is an operand, so I will push it inside the stack. And now I have an operator, that is the minus sign. So whenever I encounter an operator, what I have to do is I'll have to pop the first two elements of my stack. So I will pop b and then a, and I will have to form an equation with a and b. So you tell me, should it be a minus b or b minus a? It should be a minus b. So when I pop the stack for the first time, this element will be the second operand and the next element will be the first operand. So the minus tells me that it should be a minus b. So after I have popped the two elements, I will form an equation with them and I will enclose them in first brackets. And then this expression will be pushed inside the stack. And I see that I am done with the expression. Once I'm done with the expression, the postfix expression, I will now find its infix form as the top element of my stack. So if I push the stack, if I pop the stack, then I will get the infix form as my answer. Now notice that in my postfix forms, there is never bracket. But however, if I convert it to its infix form, then I will get an extra pair of brackets. This equation was given as an example in the previous lecture where this infix notation was converted to its postfix form. So now we will try to do the opposite. We will convert its postfix form to its infix form and see whether our answer matches with the actual answer. So the rule is I will parse my postfix expression, and whenever I see an operand, I will push it inside the stack. So this is an operand A, it will be pushed inside the stack. Then B, operand, it will be pushed inside the stack. Then C will be pushed inside the stack. So will be D, as it is an operand. And E, which is also an operand, will be pushed inside the stack. Now I have encountered an operator, which is the division sign. So whenever I receive an operator, I will have to pop the first two elements in my stack. So first I'll pop E and it will come after the division sign. And then I'll pop D and it will come before the division sign. And D divided by E is my expression. I will enclose it in first brackets. And I'll push this expression back into my stack. So now the top of my stack has the expression D divided by E enclosed in first brackets. And then I'll keep on continuing parsing my postfix expression. Now I have received a minus operator So upon receiving an operator, I will pop my stack twice. So when I pop it for the first time, this expression will go after the minus sign, and this, and next when I pop it, this element will go before the minus sign. And I will enclose them in first brackets, and I will push this content back into my stack. And then I'll keep on parsing my postfix expression. So after minus, I will have received a multiplication operator. Now since I received an operator, I'll have to pop my stack twice. So first time I pop, this expression will come after the multiplication sign. And then the next time I pop my stack, this element will go before the multiplication sign. And they will be enclosed in first brackets and pushed back into the stack. And then I'll move on to the next character, which is the plus operator. So since I received an operator, I'll pop my stack twice. This expression will come after the plus sign, and this element will come before the plus sign. And they will be enclosed in first brackets and pushed back into the stack. Alright, now that my postfix expression has ended, I now know that the top of my stack will have its infix expression as the top element. So if I finally pop the stack, then I will get my infix notation. So now if you notice that this equation might seem a little bit different from my previous equation. Now equation wise, they are both the same. They both will yield the same answer and same expression. However, I see that there are some unnecessary brackets in my expression, and that is the only difference. Other than that, these two equations are exactly the same. So we can see that when we convert from a postfix notation to its infix form, we do get some unnecessary brackets in our result. Now you might have a question that why do computers use postfix form to evaluate equations? Why when we give the input in infix form, it converts to its postfix form? This is because postfix forms are easier to calculate, easier to compute than infix forms, because postfix forms are much more straightforward. No precedence of operator is needed. Also, there is no bracket. There are no brackets. So postfix forms are much easier for computers to deal with. So let's learn how postfix forms are actually computed inside our computers. So this is the infix notation, and this infix notation's equivalent postfix form is this expression. Okay, so evaluating this infix form gives us 13, and let's see if I evaluate the same equation postfix form whether we get 13 or not. And the process of evaluation is pretty much the same as we have seen before in the conversion from postfix to infix. So the rule is, let's assume that these are single digit operands. Whenever we see an operand, we will push it inside the stack. So first we see 6, it's an operand, so it will be pushed inside the stack. Then we have 7, operand, pushed inside the stack. And then 3 will be pushed inside the stack. Then 8, and then 4. And now I see that I got a division operator. So whenever we see an operator, we will have to pop our stack twice. So 4 will go after the division sign and 8 will go before the division sign. Now instead of pushing back the expression, what we will do is we will calculate it. So 8 by 4 is 2, and we will push the answer inside our stack. So instead of pushing back the expression, we will push the answer of the expression. So 8 by 4 is 2, and then 2 will be pushed inside the stack. And then I will continue parsing my postfix expression. After the division sign, we have the minus operator. So upon receiving an operator, we will have to pop our stack twice. So 2 will be popped and it will go after the minus sign, and then I will pop my stack again and 3 will go before the minus sign. Now we will compute 3 minus 2. 3 minus 2 is 1 and 1 will be pushed back inside the stack. And then I'll move on to my next operator, which is multiplication. So I'll pop my stack twice. 1 will go after the multiplication sign and 7 will go before the multiplication sign. And we will compute 7 into 1, which is 7. And 7 will be pushed inside the stack. And then I will move on to the next element in the expression, which is the plus operator. So again, I will pop my stack twice. 7 will go after the plus sign, 6 will go before the plus sign, and then I will compute them. 6 plus 7 is 13, and I will push the answer back into my stack. Now I see that my expression has ended. So when my postfix expression has ended, I know that my final answer is on top of my stack. So if I pop my stack, then I will get the answer 13. So this has given me the correct answer. As we can see that the infix notation's answer was 13 and the postfix evaluation also gave us 13. So this is correct. And this is how postfix expressions are evaluated inside our computers.